So I'm just going to walk you through the answers to these questions that we were doing on worksheet number 1 yesterday, that were assigned at the end. So after you've taken your pictures and submitted your questions and submitted your answers, I want you to take a look at these and make sure that you understand all the answers. So, firstly, for number 4, where does the energy that leaves the system go? How does this energy transfer to affect the room temperature in the kitchen? Do you have any experience to support your answer? So, what happens with the refrigerator is once it pulls the heat out of your food, it has to dump it somewhere, and so it uses some fans and some pumps to push that heat out into the kitchen. So, normally there's kind of a warm spot near your fridge. That heat is coming from your food. It's kind of interesting. The effect that that's going to have on your kitchen is your kitchen warms up. So that's what happens to the heat in your food. It ends up in your kitchen. For number 5, one of the ice cubes that's described in number 3 is put in a glass of room temperature soft drink. Do separate bar charts for the ice cube and the soft drink. So there's my ice cube and my soft drink. And what I have described is that I'm going to have my ice go from 0 degrees to 25 degrees. So it's going to have an increase in thermal temperature. It's also going to move from ice to an ice solid water to liquid, and so my phase energy is also going to increase. When I draw my LOL chart for that, I just started all of my bars at 2s. I have energy that's going into that system because my phase energy and my thermal energy are both increasing, so energy has to enter the system so that at the end I have more energy than I started with. My soft drink is going to basically do the opposite of that. My soft drink is the reason these are low is someone asked, can we just have a bar set at 0 if it doesn't change? Well, sure, it doesn't matter. We're just looking at the change between these two. So I started my thermal energy and phase energy both at 2. There's energy that's leaving my soft drink and going somewhere. We happen to know that it's going into the ice, but it's going somewhere. And the net result is that my thermal energy is going to drop. There's no phase change in my soft drink. My soft drink isn't going from a liquid to a solid, it's all staying liquid. So the only one that's going to change is my thermal energy. And we were having a discussion here in class because initially uh, I had only removed 1 square's worth of energy. And so they said, well, that's not going to match what happened to the ice. So we made it match and shrunk it down. So that's why there's an X over it, because in the end we decided it should be 0. Oh, and this is because my arrows look like the rocket ship from Kung Fu Panda. But anyway, the ice cubes in the end are going to have particles that have much less motion um, as a solid than they do when they melt and increase in thermal energy. So they start out with less motion and then they increase in energy. The soft drink does the opposite thing. It starts with more motion, and as it collides with the ice cube and loses that energy, it's going to have less motion in the end. On the second page, you guys are in a tricky spot because normally I've done a lab activity here for this one, but what ends up happening is that the more water you have, the longer it takes for that change to happen. And so here we have a cooling curve for a substance as it freezes. So you can imagine the difference between having a puddle and having a lake. It's going to take a lot less time at a cold temperature for a small puddle to freeze than it would for a large body of water. And the reason for that is because water has a high heat capacity. Heat capacity is the ability of any kind of substance to absorb energy. For water, it's actually quite high, which is good for organisms. But what it means for this question is that if we've got a larger sample of the same substance, you're going to have to push more heat out of it to be able to get it to cool so that it can cross this boundary at 0 degrees from a liquid to a solid. We're either going to do this activity in class or we're going to do it on Pivot Interactive. So you guys will get to see this in action. The particles during each portion of the graph, up here we've got liquid where the particles are moving rather quickly. When we're doing this temperature change, or sorry, this phase change here, we have some particles that are moving quite slow compared to others. They're not necessarily all the same. And then once all of them are a solid and they've all slowed down substantially, then we can start to cool the temperature again. So I hope that helps you guys understand what's going on with those. The thing that will be assigned to you tomorrow is worksheet number 3, which is more LOL charts. You guys know all the information that you need to be able to do an LOL chart. So if you would like to make good use of the time that you have today in class, go ahead and take a look at some of those. We'll start tomorrow talking about these. But if you do them a little in advance, you might ask better questions, and it'll also mean you have less to do tomorrow. So I'm sad that I'm not seeing you guys today, but I will see you tomorrow in Google Meet on our remote day. I hope that you guys all have a super great day, and I'll see you tomorrow. Bye.